Greetings. I was asked to talk about the first part of the module this week, and it starts with a discussion about angles, and I have a few sketched on the screen right here. Students will come into this lesson knowing a few things. They will already have previous knowledge about rays and probably vertices, but they probably won't have a great understanding of how we measure angles. Which is why I think it would be beneficial to start a discussion about how we measure angles with a circle on the XY plane. Once the students have an understanding that a circle has a measure of 360 degrees, and we can refer to that as an angle with a complete rotation, we can start defining angles that do not have a complete rotation. We can talk about acute angles, right angles, and obtuse angles, and we can provide definitions for them. On the right side of the screen, I tried to create an image to kind of show how we make these various angles. So we have this ray BC. We have this character pushing up to create an angle BCA, which would be acute. And we have this other figure pushing a little bit further to create BCE, which is an obtuse angle, and if we were to push it even further, we'd have a straight angle measure of 180 degrees. And I believe it would be beneficial to start with the concept of a complete rotation and then work backwards. Next, I was asked to talk about the sum of interior angles of a triangle. This figure allows students to use the previously learned material in basic rigid motion and congruent angles and angle relationships. Students may not automatically know that the sum of interior angles of a triangle are 180 degrees, but they do know that a straight line has a measure of 180 degrees, and they can use the three angles that comprise the straight angle to demonstrate or prove the theorem that the sum of interior angles of a triangle is equal to 180 degrees. Specifically, they can use basic rigid motion to demonstrate that we can map angle A to coincide with angle B through translation, and we can map angle B to coincide with angle D through rotation. And they can use that knowledge to prove the theorem. Next, I was asked to talk about pentagons, and I believe in a straightforward approach when teaching polygons. How we name them, some of their characteristics. One point of emphasis I would make would be the diagonals, because they allow us to do a lot of things, especially when we transition to the sum of interior angles of a polygon. And we have our formula, and if we use our pentagon here and we make our two diagonals, we realize that we create three triangles, and we know the sum of the interior angles of a triangle is 180 degrees, and therefore if we multiply 180 degrees times 3, we can find the sum of the interior angles of the polygon. And helping students realize that the number of triangles we create depends on the number of sides the polygon has. And that's where this number in the parenthetical comes from. There will always be two less triangles than there are sides. So if we have a 6-sided polygon, we have 4 triangles, and as up here we have a 5-sided polygon, we have 3 triangles, and that's an important relationship. Lastly, I was asked to talk about the sum of exterior angles of a polygon. This is not something that I've taught or thought about a lot, or discussed at length outside my mind. But I believe this is a good opportunity to show, or to allow students to use their knowledge of linear pairs to to prove that the sum of exterior angles of a polygon will always equal 360 degrees. We know that if we treat the exterior angles as the remainder of the linear pair, i.e. 180 minus the interior angle, we'll leave this remainder, the exterior angle. And we add or sum all the exterior angles and subtract it from the interior angles, we should achieve a value of 180 degrees. And knowing that the sum of the exterior angles of any polygon equals 360 degrees is another important relationship. And that's all the time I have. Thank you.